And while we're opening to page 15, can I just get a sense from the people who are here? How is the chain rule treating you? Homework was hard. Yes. Yeah, the homework is hard. It's a lot of details. I like the word meticulous that Ernie just used. We're going to write down a few shortcuts today, right at the start of class, that maybe will help you do the chain rule homework. So it's okay if you didn't get the whole thing done. Turn in what you have, and we'll give you credit for it. It's not a matter of getting the chain rule at this instant or last night or 2 days ago. It's a matter of having it by next week. That's the goal, okay? And I think I had mentioned that with this calendar up here between test 1 and test 2, it's a whole slew of derivative techniques. The most important derivative technique you will ever see in my class or any other is the chain rule. Okay, so it is a big idea. It is a really important idea. We're giving it 2 full days of our attention, and we're going to be using it. I got to say, probably every day from now on, we're going to be using the chain rule at some point in class. It really is the most common rule that you'll ever use in terms of derivatives. So we'll take a quick look at the calendar, and then we'll dive back into chain rule stuff and see if we can clear up some of the confusion. So today we have a lot of stuff happening. First, project number 3 is due today, so hopefully it's in the folder. And second, project 4 is assigned today. So, Ernie, do you mind walking around and putting about 5 of those on every table? Thank you. Okay. Yeah, that's what it is. I mean, the calculus version of just changing the letters to make it easier to handle. And that was Leibniz's version of it, where we use Z just to make it easier for us. But one other thing, the quiz that we had last class, you remember, became a take-home quiz. So put the finished quiz in the folder this morning. Okay, so we're going to finish up chain rule today on Monday. It's another review day. You can see we're here in chapter 1 again. So the idea is after a couple of days of intense calculus with the chain rule, Monday hopefully we'll take a little bit of a breather reviewing the trig functions. So we won't do any calculus on Monday. And then on Wednesday next week, we'll talk about derivatives of those trig functions, and then we'll take another step backwards, really just trying to keep the pace manageable. We're back in chapter 1 on Friday to talk about inverse functions and review log functions, and then we come back and do some more calculus the next week, okay? So it's going to be kind of for the next few days, a day of calculus, a day of review, a day of calculus, a day of review. So hopefully the schedule will work for us. All right, so again, we're here on page 15. But before we dive into page 15, I have a resource that I just learned about yesterday that I wanted to share with you all. And the resource is this thing that GCC now subscribes to called Smart Thinking. And what it is online tutoring. It's something that costs GCC some money, but will not cost you any money. I've given you guys a piece of paper that says Smart Thinking on top. Go ahead and grab one copy and take it home with you. It has all the directions for how to log in and a little bit of the details. I'm going to try to give like a 90-second version of what this thing is, and if you want more details, see me right after class or just play around, okay? So there's a website you can go to, or if you just Google Smart Thinking, it will come up. So if we go there, there's a login page over here on the right-hand side. And the login for you, and again, it says this on the sheet that you just got, but it's your GCC email address, and then the password is GCC. And once you go in, I think it'll prompt you to change it. So mine doesn't look like that anymore, but I'll type in my username and password if I can remember it. I think you do have to put the @StuMail stuff. I do, but I've changed my password or my username from the default, but I believe it is with the StuMail and all that stuff. So here's the idea. I'm going to show you a completed thing. I actually went online yesterday to test this thing out, and I got a tutoring session in calculus. So I will show you the result of that tutoring session. Again, it's all on the internet, so there's no talking. All the communication is through through typing and with math tools and stuff. So everything in black is what I wrote. Everything in red is what my tutor Mary wrote. And so I said, "Can you help me with the chain rule?" And I said, "I'm trying to find the derivative of sine of x squared minus 5x." And so she doesn't just say, "Here's the answer." If she just says, here's the answer, it's kind of a waste of everybody's time. So she says, have you worked on this? I said, yeah, I think I know I have to use the derivative of sine, but I don't know what to do about the stuff on the inside. And so she gives me this formula, which should look kind of familiar. It's a specific version of the chain rule. We don't really know that sine goes to cosine yet, but anyway, she asks kind of leading questions and gives hints, and she ends with a lot of smiley faces and winky things. I don't know. That was fine. Okay, and so then I made a mistake here when I said, here's my answer, and she said, well, this part is good, but this part we need to fix. And she tells me what I'm supposed to do, but doesn't tell me what the right answer is. And so again, it's kind of a Socratic method type thing where she's not going to just give you the answer. She's going to ask you sort of leading questions and get you there. And I thought it was really, really quite good. Hello.
Do you have any extra folders for testing someone?
More?
What do I have to bring back to you?
I don't know.
Okay,
I mean, I don't need them today, so you can take them all today if you want. Okay. No problem. So that's fine. And then I gave her a more complicated one, and she gave me some more hints, and we went on to another page, and then we finished. And again, it's just this kind of back and forth. And I thought she was very knowledgeable, and I thought she was very supportive, and I thought it was good. She made one small mistake, but then she fixed it like 30 seconds later. It was fine. It was totally fine. So here's what you have available to you. If I go up here to my account, it will tell me that I was given a total of 70 minutes to use. I have used a total of 30, so I have 40 minutes available. Every GCC student has been given a total of 5 hours of tutoring time. Everybody, 5 hours of tutoring time. And so what you do is you go you log in, and it comes up with this page right here. You're going to use this stuff on the left-hand side. So first, there's a bunch of subjects where there are tutors available right at this moment. That is the current list. It's kind of early in the morning. If you wait throughout the day, that list will get longer as the tutoring becomes more available in more subjects. And then in the middle of the night, it'll get shorter again. If you just want to know what the schedule is for all the subjects, you can click on live hours and take a look at the subjects page. Actually, that's not right. Take a look at the view all schedules page. And it tells you that all of this kind of math is available 24 hours a day, 7 days a week. If you need bilingual, like a Spanish math tutor, that person is available these hours, and you can keep going. Accounting, there's science, there's reading, there's writing, economics, and a whole bunch of other subjects. So the 5 hours that you have been given is not just for math, it's for any subject that you want. And so obviously I'm sharing this because of the math stuff, but you can use it for anything at all. And so I'd encourage you to just go in here and play around. Let's go back to this thing. I think we logged in, so it should be fine. Okay, so I'm not going to click it, but if I wanted help in calculus right now, I would click this, and it would open up another window, and it would connect me with the tutor, and we would just start with whatever I wanted to start with. Okay, Todd. You don't have to pay for it. If you use up to 5 hours, there's somebody on campus that you can contact and say, hey, can I get more time added to my account? I don't know who that person is at the moment, but it will become clear. There'll be a little thing that pops up and says, hey, you're getting close. You might want to contact so-and-so. And what that person would do, I want to say it's almost an automatic, sure, you could have more time, but they'll just take a look at what you've been doing and how you've been using the site. And if you've been using it the way it was intended to be used, then I think you'll be given more time. It won't cost you anything. Good question. It might be Mary Ellen over in the Learning Center. It might be Michelle Bartholomew. It wasn't clear yesterday when that question came up. Yeah. Okay, so that's that. And I do want to just say one other thing here. You can also get help with writing. There's a whole bunch of different kinds of writings that you can get help with. If you have an essay, if you have a resume or cover letter, if you want to write something about career stuff, Spanish Essay Center, and then paragraph submission. And I think I can show you one very quick example of what it looks like. Where do I go for this? My home page. I was looking for a link that, here it is. On the main page, there's this thing called Services and Subjects where you can actually take a look at some sample sessions. That's what I want. And for example, this writing tutorial, you can click on it and it'll show you kind of a fast forward video of somebody asking questions about this writing assignment that they had. So there's one way to get help with a writing assignment. Another way to get help with a writing assignment is to just submit a paper that you've been working on, and they will come back, and within 24 hours somebody will give you feedback on that paper that you've written. If you wanted to have a look at what that looks like, there's these orange things on your desk. Please don't take it home, but I did want to just show you there's some sample things at the end of this orange booklet. So for example, if you could just open to page 10 in the sample booklet, I'll just show you a writing example. Everybody open to page 10 and just kind of share this book. So on page 10, you will find an essay that somebody's written. And all of the stuff in bold are the comments that the writing tutor has come back with. And you'll notice, I don't know if you have a chance to read any of these things, but you'll notice it doesn't say, oh, I fixed this word and I've changed the tense in this sentence and this needs to be less passive and more active. It's just suggestions. This tutor has not made any changes to the essay, just made observations and suggestions to try to make the essay stronger. And I think that's a really, really good way to get help. So anyway, I think that there's a lot to be said for this resource. Again, everybody has 5 hours. Go play with it. You got nothing to lose. Again, your username is your GCC email address, and the password initially is GCC. And all that is written on that piece of paper that you can take a copy of right now. Any questions on this? Okay, so we'll close this and let's start doing some math. Okay, so we're on the bottom of page 15. And at the very, very bottom of page 15 is some version of our new favorite derivative rule. It's the chain rule. It deals with composition of functions. So it says if you want the derivative of f of g of x, you do f prime of g of x times g prime of x. That's the symbols way. Here's another way to think about it, getting a little less symbolic and a little more informal. The derivative of f of stuff. Instead of f of g of x, we'll just call it f of stuff. It's f prime of the stuff. You can see hopefully that f prime of the stuff matches with f prime of g of x, yes? And then the second thing, let's see, it's supposed to be g prime of x. Well, that's just the derivative of the stuff. And I'm a big fan of using the word stuff. I get away from the symbols and I get more towards something that I can understand. And so I just want to take a quick look before we move forward. I want to go back one page where you guys went and did a lot of these practice problems towards the end of class yesterday. So if we jump back to page 14, I think that a lot of you have answers to most, if not all, of these questions here. I'm not going to write out the answers to these questions, but I am going to give you kind of little shortcuts, ways that I see the chain rule popping up here, because in my mind, I really don't see F's and G's or Y's and Z's. I have very, very informal rules in my mind that guide me through the chain rule. So here's what I see for this problem. I see the square root of some stuff. I don't care how complicated that stuff is. At its heart, this is the square root of something with x. That's all that I see. And if I see a square root, I immediately translate it to what? I translate it to the 1/2 power. Because I can handle 1/2, x to the 1/2. I can deal with the derivative of that. So let's start talking now about a new version of the chain rule, a specific version of the chain rule applied to stuff to a number. So here's my new derivative rule, the derivative of stuff to a number. Maybe you can find some place to write this. I'm going to give you guys 4 little shortcut rules, and then hopefully you'll see the pattern and be able to come up with your own little shortcut rules. Okay, if it was just x to a number, we would know what to do. What would we do? Number would come down, power rule, right? Number, so that's what you do. Number comes down, subtract 1 from the number. Normally in the parentheses is x. What goes in the parentheses now? Stuff, whatever that stuff is, it just goes in there. And all of that is the power rule. That's the derivative of the outer function. That's the f prime. But then the chain rule comes in and rears its head, and it says you always have to multiply by the derivative of the stuff. And that thing I'm going to write in green at the end of every one of these shortcuts. This is what the chain rule says. You do your basic rule, but then you pay for it by multiplying by the derivative of the stuff. That's going to be a constant for all of our shortcuts. So in our case, maybe you guys have the answer already written out, but if you have a final answer to this derivative problem, see if you can find it. You should see, before simplifying, 1/2 in the front. You should see the stuff copied, that entire fraction as is, unchanged. What's the power? What's the new power? Is negative 1/2. Do we see that? If you've got this problem done, you should see that somewhere. The 1/2 in the front, the whole fraction, all that stuff copied, negative 1/2 is the new power, and then times over here in green, the derivative of the stuff. The stuff in this case is that fraction. And what rule do we need for the derivative of that? That's a quotient rule. So you'll see a big quotient rule. I'm not going to go into the details of that. That's old. But right there at the end, you'll see the quotient rule. And so I'm going to highlight in yellow the stuff every time. Let's take a look at number 2. Number 2, I will tell you what I see. Again, I kind of put like pseudo blinders on and I cross my eyes a little bit so I can't see all the details because there's a lot of details. It's easy to get lost. Here's what I see. Sine of stuff. At its heart, this is sine of something complicated. That's all that I see at the start. And so let's write down a new little shortcut for the derivative of sine of some stuff. Okay, so we officially have not seen this yet. We're going to tackle trig derivatives Wednesday of next week. But I wrote this rule down up earlier on this page. What's the derivative of sine of x? Cosine of x. So if the derivative of sine of x is cosine of x, then what do you think for the start of the derivative of sine of stuff? Cosine of stuff, right? Sine of x becomes cosine x. Sine of stuff becomes cosine of stuff. That's the f prime. That's the outer derivative. But we always need to tack on at the end the derivative of the inside. And so again, in green, I'm going to write this same exact thing every time you need to multiply by the derivative of the stuff. So this one was a lot easier than the one up above. See if you can find your answer to this one. What you should see is cosine of t squared. That's the stuff. And then the green times the derivative of the stuff. I will highlight the stuff in yellow. What is the stuff? T squared. So what you should see at the end is the derivative of t squared. That's 2t. Let's take a look on the next page. Okay, again, kind of putting my blurry eyes on. First and foremost, what do I see here? I see something with x times something with x. That's all that I see. So what rule is that? That's a product rule. So not only do we need to know product rule, quotient rule, chain rule, trig derivatives coming soon, but we need to know in what order to apply them. So just because we're in the chain rule section, don't just start thinking about chain rule derivatives. You got to ask yourself, what is this at its heart? It is the product of two things with x. That is all. And in the midst of doing the product rule, at some point, I'm going to have to find the derivative of the second. And when I see the derivative of the second, this 2 to the x squared, in my mind, I start putting the kind of blurry eyes on again, and I say, oh, this is really 2 to some stuff. And let's write now a new rule for the derivative of a number to some stuff. So just to remind ourselves, derivative of a to the x is a to the x, but this is not a bring the x in the front. This is a number to the x times natural log a. That was our rule. We introduced it a few days ago. All right, it's the same rule. It's now a number like a, but now instead of x, it's some stuff. So let's write down the derivative here. A to the x becomes a to the x. How about a number to the stuff? Number to the stuff. We can follow these patterns here. Number to the stuff. So you just copy it. But then in green, oh, sorry, not done. Still in blue, what's the rest of that derivative rule? Times the natural log of, yeah, is it the stuff or is it the number? It's the number. A to the x becomes ln of a. Number to the stuff becomes ln of the number. But then in green, we have to pay for it. The chain rule always says what goes at the end? Derivative of the stuff. And so we will again highlight in yellow 2 to the x squared. What's the stuff? It's the x squared. That right there is the stuff. If it were just x, I could handle it no problem. Because it's more complicated than x, it's the chain rule. So somewhere on your paper, I'm not going to say the whole product rule part out, but just for the derivative of that second term, you should see, okay, let's see, number to the stuff becomes number to the stuff. So 2 to the x squared, you should see 2 to the x squared times ln of 2, not the x squared, just the 2, but then times the derivative of the stuff. What's the derivative of that yellow? 2x. At the end of that one term, you should see it 2x. Okay, let's take a look at 4. Tangent squared of t. All right, first of all, we need to make sure we're really clear about what that means. Those symbols mean tangent of t squared. That's not calculus, that's what the symbols mean. So hopefully you saw that in a pre-calculus class. And once I see that, again, I put my kind of blurry eyes on and I see stuff to a number. That is what I see. And I'm not going to write it again because that rule we did on the previous page. That number is going to come down. You're going to copy the stuff. You're going to subtract 1 from the power. And then you're going to stick on that green derivative of the stuff. Stuff in this case is tangent of t. Again, we don't officially know it, but I gave you a little hint up here. It says derivative of tangent is secant squared. So you stick that at the end, and that is all. Yes, number 3, it's for me, I start doing the product rule, and at some point in there, I say, oh, shoot, I have to do the derivative of this complicated thing up here in black. And then all that comes back.
Yeah, I noticed in one of the homework problems that the variable they used was z.
Mm-hmm.
And I was doing like the z equals y equals thing, and I realized after I'd done the problem, it probably is better to see this.
It's, you know, I mean, it's, you just have to be careful that you don't get so married to only one way of seeing it that you get kind of stuck if they use letters that don't match with the letters you want to use. Yeah, it can be real confusing. Okay, last rule. I said there were 4 rules. We've seen 3. Here's the 4th one. The 6 in the front, I don't really look at. E to the stuff. That is what I see. And so let's start writing out a derivative rule for e to the stuff. This will be our last shortcut for today. Todd? Yeah, I mean, e to the x becomes e to the x, right? So it seems reasonable that e to the stuff would become e to the stuff. But then in green, what do we tack on every time? Times the derivative of the stuff. So this one is short enough. We'll just write out what the derivative is here. You can check your answer. That 6 is a constant multiple. Does it stay or go when I take a derivative? Stays. Constant multiples stay. Constants floating by themselves go away. 6 times e to the stuff becomes e to the stuff. We copy it. E to the 0.013t. Copied. But then in green, times the derivative of the stuff. The stuff in this case is up there. It's a little bit too big. Only the power. That is the stuff. What's the derivative of 0.013t? It's 0.013. That's the answer. So last class we talked a lot about f's and g's and about y's and z's, and now today I'm coming clean. I don't think about any of those letters for finding derivatives when you give me a formula. That said, I didn't want to just present a list of like shortcuts that don't seem to have any kind of common thread through them. They all follow from the chain rule. But here are some specific examples that come up over and over again that you're hopefully going to get to a point where you don't think about the F's and G's every time. You'll get to a point where you just say, oh, I've seen this specific kind of chain rule before. Let's just go for it. Okay, so if we're ready, we'll go to the next page. And we're going to do some problems. Actually, I kind of want to change the order a little bit. Let's go another page down the road to page 17. All right, page 17 says find the derivatives of these things. So first one, e to the 5x plus 2 squared. So I want us to start thinking about these little shortcuts that we've just written. So I'll just write out just the things that we just figured out how to find the derivative of. We had stuff to a number. We had a number to some stuff. We had sine of stuff. And we had e to the stuff. And there's nothing special about sine, like could be cosine of some stuff or tangent of some stuff. We'll get to all of the trig function rules soon enough, but we'll just focus on that one for now. So basically we've got 4 shortcuts we just saw. Can you guys identify? We have 3 of them here, A, B, and C. Those 3 are each one of those 4 things up at the top. So can you kind of match and figure out which one matches with which one? So go ahead and chat with your neighbors, see if you can identify which goes with which. Okay, let's mix and match. Part A, what kind is part A? Yeah, it's actually going to be 2 different things. So first thing, if again, we're just all kind of blur your eyes a little bit, you're going to see E and then something complicated. And then we'll deal with the complication soon enough. You're right, Abby, it's going to be 2 different chain rules here. But first, it's an E to the stuff. How about the next one? That is stuff to a power. When you see a square root, you are going to immediately change it to a 1/2 power, and then it becomes something that's starting to look more familiar. How about the last one? That is also stuff to a power. You're going to see stuff to a power come up over and over and over again. So this is the first task, is to identify what the basic rule is. So I think we've got that done. And let's see if we can start applying it. We'll go here to part A, E to some stuff. Remind yourself if you need reminding. You just wrote down some rule that says the derivative of e to the stuff is something. So the derivative of e to the stuff is e to the stuff, and then we'll talk about the green. So it's just e to the stuff. Use good notation, y prime equals. Don't just put a derivative, put a y prime equals. E to the stuff. So we copy it as is, e to the 5x plus 2 squared. And then I'm going to write here in green times the derivative of the stuff. The stuff in this case is what part of that? 5x plus 2 squared. I'm going to highlight that stuff in yellow, trying to be consistent. And then I'm going to write here in green, derivative of 5x plus 2 squared. Just acknowledging that I need to tack on the derivative of the stuff. And at some point, I don't need you to write that step. In fact, I don't ever need you to write that step, but this is the first time, I think, that we're seeing a chain rule within a chain rule. And so I'm just showing you it comes from like the basic rule we wrote down just a few minutes ago. But now Abby points out that when we're trying to find the derivative of 5x plus 2 squared, that's a whole new rule looking at the top. Which one is it? It is a chain rule. Which one? Is it number to the stuff or stuff to a number? The stuff to a number. 5x, you see x's, that's what I'm calling stuff. So that's 5x plus 2 squared. That's another chain rule. It's a different chain rule. Stuff to a number. So let's copy the first part. That's just hanging out, waiting for us to finish. E to the 5x plus 2 squared times. And now remind yourself, look at the previous page. What's the rule for stuff to a number? What do we do? We bring the power down. This is our power rule. So what comes down in the front? It's a 2 times the stuff. So don't change that. That 5x plus 2 is sitting there. What's the new power? 1. And then I'm going to really show details here and say times the derivative of some stuff. But the stuff has changed. What is the new stuff for this stuff to a power? It's the 5x plus 2. So I'm not sure what's going to happen with my highlighter. Let's try. There we go. That is the new stuff. And so the thing that plays the role of stuff has changed. There's a different chain rule that we had to apply. Chain rule twice. Right. The first rule that we had here was e to the stuff. And in the midst of doing that, we ended up finding the derivative of 5x plus 2 squared, and we say, oh my gosh, that's another chain rule. So now I have to just start over like it's a brand new derivative problem and apply that chain rule for the 5x plus 2 squared. And that involves the derivative of 5x plus 2. And so we're going to see this kind of multiply, multiply, multiply happening whenever we have repeated chain rules. Because every chain rule says multiply one more time by some stuff. So I will write our final answer down here, e to the 5x plus 2 squared times 5x plus 2 to the first times. And then finally, what's the derivative of 5x plus 2? 5. That's our final answer. Okay. So again, I'm not going to ever require you to write this thing in green, this ddx of stuff, and keep copying that, but I would encourage you to do it until you're really comfortable. When you get comfortable with it, hopefully we'll get to a point where you just see the original problem and you can write out the final answer just in one fell swoop. That's the goal. Okay, let's try part B. All right, part B, we're going to need far more room than we have here. We'll take part C's space and then C will go somewhere else. So again, what's the rule here? This is really stuff to a number. So I'll kind of abuse this and just, instead of the square root, immediately we translate it to 1/2 power. And stuff to a number, you've got the rule. Look at it if you need to refresh your memory, but it is the power rule. So what comes down in the front? The number comes down in the front. So y prime equals 1/2 comes down. What goes in the parentheses? All the stuff. E to the sine of 2x minus 4 cubed. Okay, at this point, I'm going to wave the white flag. I need more space. So let's just try this over here. So can somebody remind me? It was the square root of e to the sine of... Okay. All right, so then we had our first rule here, what y prime is, so that became a power. 1/2 came down. We copy all of that stuff. We don't think at all about taking derivatives in there yet. We're just doing the chain rule version with a power. So that's cubed, that's there. What's the new power? Negative 1/2. We subtract 1 from the power. And then we need to put times, here in green, derivative of the stuff. So I'm going to highlight, what is the stuff in this problem? Is it just the sign? It's the whole thing. It's all of this. We did some stuff to the 1/2 power. The stuff was everything inside of that radical. All we dealt with was the 1/2. We haven't dealt with the e yet. We certainly haven't dealt with the sign yet. So it's the derivative of all that. So we're going to write all that over here in the parentheses. And you might start to get a sense of how big this problem is going to be by looking at all the things that we have yet to deal with in the green.
You gave us such a little box.
I did. That was misleading, wasn't it? Yeah. Okay, equals. So we're going to copy this first part, 1/2. I think things will start getting smaller as we copy them because we need more room. 2x minus 4 cubed, negative 1/2. So far, so good, times. Now we have derivative of all that. This is a separate chain rule. Joe, okay? Yes, that's the power rule. Okay, this is a brand new chain rule here in green. E to the stuff, that's the translation. What Tony just said, I want you guys to translate. It's very complicated, but I want you to break it up into one of our simple versions of the chain rule. So far we have 4 of them. That's e to the stuff. And what's the derivative of e to the stuff? Is e to the stuff, and then times derivative of the stuff. So we write down e to the stuff, e to the, all of that. I do. I apologize. Okay, times. So this was an e to the stuff. What's the stuff if I'm seeing this as e to the stuff? All of that. If I see this as an e to the stuff is now highlighted in blue. So here at the end, in green, multiply by the derivative of what? Sine 2x minus 4 cubed. There. I think I'm going to run out of digital ink on this problem. It's so long. Okay. We proceed merrily along. But we're going to start saving some space. All of this, imagine in your mind, is right there. Let's just focus on the new derivative here. That's a brand new chain rule. We have 4 of them. Which one is this? Sine of stuff. That's what we have, right? Sine of stuff. Okay, I can handle sine of stuff. Sine of stuff. What's the basic derivative of sine of stuff? It is cosine of the stuff. So I'm going to put cosine of. What's the stuff now? Yeah, it was sine of stuff. So I guess everything that happens after the sine, that's the stuff. So it's cosine of all that. 2x minus 4 cubed. And then we need to do the derivative of the stuff. So times derivative of, what's the latest stuff? Is that 2x minus 4 cubed? Boy is right. What makes this so challenging is that you have to continually update in your mind what is the stuff, because it changes. At every level of this derivative calculation, it changes. So now we are doing 2x minus 4 cubed. That's one of our 4 basic chain rule examples. What is this? Stuff to a number. We can handle stuff to a number, and finally, you can actually see that the stuff gets simpler and simpler every time, right? Like every time we go, the stuff gets simpler. So eventually you get to one where it's just, okay, finally it's just one last derivative calculation and we'll be done. So equals, use your imagination, all of this, including the stuff I didn't write down, is there. And then finally times the derivative of 2x minus 4. 2x minus 4 you said was stuff to a number. Highlighted in yellow is the stuff. So what's the derivative of stuff to a number? What do we do? Bring down the 3. Copy the stuff. 2x minus 4. It is very tempting to just put a derivative in here and say it's 2 and call it done. It's not. You always copy the stuff. What's the new power? Squared times. One last green thing. Derivative of, what's the stuff? Is the 2x minus 4. And we'll just write down what this thing is in one last calculation. What's the derivative of 2x minus 4? 2. Whew, I'm winded. I need to do some more cardio because that was tough. Yeah, simplifying something like that is not something we'll ever be asked to do. We'll have simpler things. Yeah.
This was like the tax
Nikki. Yeah, and I think, I mean, like, I have a lot of colors up here. I don't know how many colored pens and pencils you have and highlighters, but I mean, I really do think it helps kind of clarify this changing role. Yes. So, good question. So why isn't, you're asking about this part or you're asking about the E part? The first or second? Which one? First part. Okay. So, all right. So the question is, how come we didn't just do stuff cubed first? And this is a good question. What we need to do is, again, kind of cross your eyes a little bit and try to see only the fundamental derivative rule that applies and not so many of the details as far as what's going on near the X. So the first thing that I see here is what? E. And then all of this up here is some complicated function of X, right? Everything up there in the power is just some complicated thing with X's. Don't dive in so early and start looking and trying to analyze what those X's are. This is E to something. That's what it is. And so that's the first rule that we have to apply. And this is part of the difficulty with these kinds of derivatives is not just knowing all these rules so well, but also getting them in the right order. There's only one order that's going to work for this. I know we like to say, all right, a lot of problems that you solve will have multiple solutions. There's one order for this. And we really have to, that's part of what we're going to be working on in terms of getting this chain rule down pat. Nikki. Yes. These are the four that work for all the ones that we're playing with today. We'll see soon enough see ln of some stuff and tangent of some stuff, but there's not going to be a million of them, but you know, maybe about another 10. But it's like the basic idea is learn some simple rule, assuming it's just X, and then we can apply the chain rule to make it complicated. Garrett.
What's weird for me about these like more complicated ones is like if you take the derivative of like a cubic or whatever, it makes it a quadratic. It's like it makes it simpler. Like I can picture the graph look like better. Whereas like some of these complicated chain rule functions, like I can sort of picture what like the square root of e to the sine, blah blah blah. You know, it's gonna oscillate in this square root, so that's positive. I can sort of picture the graph of that with the derivative. I cannot picture what the graph of the derivative, which is weird that it's getting more complicated.
Yeah.
Maybe a simplified answer, easier to imagine.
I don't think so. I think that the power rule is deceptive in that it's one of the few derivatives that gets simpler. I think that that's the outlier, not this one.
It's going as of like a couple weeks ago. I was thinking derivatives is way to simplify.
Right. But then imagine even when we had our product rule come in.
Yeah.
A product just has two things multiplied, but when you do the derivative, how many pieces are there in that derivative?
Right.
There's four of them, right? First derivative of the second, second derivative of the first. So as a rule, derivatives get more complicated when they're more complicated than the original function. I think power rule is one of the few exceptions to that. Yeah, it's a good observation. Okay, so that is as hard a chain rule as I will ever give you. This isn't like building to something worse. Like this is the worst one you will ever see, okay? So if we can handle this one, we can handle them all. I like this in that it tackles like a lot of our four different rules. I had a friend back in high school. I took AP Calculus as a senior in high school, and my friend Matt, you know, like so we're doing chain rule stuff. I don't think we ever did things as complex as this one, but we were doing chain rule, and I was helping him out because well, not to brag, but I was pretty good at calculus when I was in high school. But he never knew when to stop. He would just keep taking derivatives. Like he would come down here, right? The derivative is 2. He would take another derivative and get 0. And like he would just always end with 0 because he would just keep taking derivatives. And really the chain rule doesn't say keep taking derivatives. The chain rule says take how many derivatives? How many, like at the very end, it would always say derivative of the stuff, right? The chain rule contributes one derivative. That's all that it does. Every layer, we took one derivative. You can see this green thing hanging out at the end. It was only one derivative. It didn't say, like we didn't know that this first green thing right here was going to turn into like 3 or 4 more derivatives. Turns out it did. But the chain rule doesn't say take 3 or 4 or 5 derivatives. Chain rule says take one. So if you just write out, take this one derivative, you won't get it wrong. You'll see that it kind of balloons a little bit if you have multiple chain rules inside, but every time we did the chain rule, you see one derivative at the end. Any questions on that? Yeah, nesting. That's right. That's right. So speaking of the nesting doll, let's go back one page, page 16. I apologize for the space on this problem. I think I told you guys at the start of the semester that the order was changed around quite a bit from the last time I took this, or the last time I taught this course. And so you guys are essentially getting version 1.0. I mean, it's different from the last one, but it's like version 1.0 of this. And so version 2.0 will have a lot more space for that problem, but you guys are the guinea pigs. What's that? Nice. Okay, so Joe talked about nested dolls. So take a look here on the bottom of page 16. So on the bottom of page 16, it says, okay, what if you have f of g of h of j of x, like four nested functions, one inside the other? How would you take a derivative? Okay, we'll start from the outside. We'll take one derivative times the derivative of the stuff. This guy is copied from up above. The derivative of this thing breaks up into two pieces because it's another chain rule. And every time you have composition, it breaks up into two pieces. And there's the last derivative going at the end. And so this is kind of the symbolic way of seeing what we just did with a specific example. If you have lots of nested functions, you're going to get lots of derivatives all multiplied together. Okay, so here's what I'd like us to do now. Right up here, we're going to go to number 2. And Lindsay, can you read number 2, please? Okay, so I came clean today and I said, when I think chain rule, I don't think F's and G's and I don't think Y's and Z's. I think e to the stuff. I think stuff to a power. I think with the word stuff in my mind. But there are occasions where I'm going to quiz and test you on knowing the kind of notational version of the chain rule without stuffs, but something very formal. So here I've given you very little information about two functions, f and g. I'm telling you f of 1, f prime of 1, g of 1, g prime of 1. Very little information, 8 pieces of information. And from all of that, we're going to ask you to find some derivatives. So let's take a look at part A together here. So it says derivative of f of g of x, and then that means evaluated at x. I think it's equals 1. It's hard for me to read on this. Okay, so we're going to find the derivative of f of g of x. Can I think of it as like stuff to a power? Can I think of it as sine of stuff? I can't think of it as any of those things because I don't have the rule for f. I just have a few isolated data points. So we need to use this thing right up here. So I'm just going to write that thing. Here's what it says. F prime of g of x times g prime of x. If we can't get to that symbolically, we have no hope of answering this question. And actually, a lot of the work is done already. As soon as we recognize we have to use that formula, what do we change these x's into? Change them into 1s. So x equals 1. Both of those x's are 1. And now we hope and pray that we have enough information at the top of this page here to figure out what all this mess is. So let's try. Equals f of, in here is g of 1. Do we know g of 1? Yes, it's 2. Times, do we know g prime of 1? Yes, it's negative 6. So far, so good? Oh, sorry. Thank you, f prime of 2. And then by some miracle, do we happen to know f prime of 2? Oh, we do. Look, it's 10. Isn't that convenient? So this is 10, negative 6, negative 60 is the answer. So far, so good? Nikki?
Totally generalized thing using all the variables in that group.
I want you to be able to do ridiculous chain rule things like this, and I want you to be able to do examples like the one we're in the middle of here, I'm not going to ask you to do, I'm not going to ask you to write this stuff out symbolically. Yeah, okay. All right, let's try part B. All right, again, we start with our basic rule, f of g of x. We have the derivative rule. It's formally written up above. So we just put f prime of g of x times g prime of x. But instead of x in this case, what do we put? Put 2. Both of them become 2. Mm-hmm. No, I want negative 60 as the final answer. The calculation that we did. So we wrote, yeah, just the calculation. So we wrote all of this out, and then we started grabbing information from up above, and then we grabbed one more thing from up above, and then finally multiplied. Yeah. Okay, let's see if we can answer this one. F prime of, all right, what's g of 2? It's 1 times g prime of 2, 5. So far, so good. F prime of 1, do we know it? It is negative 2, convenient, times 5. Negative 10 is the answer. Okay, so is this the most exciting thing to do? No, I mean, like, I think the crazy chain rule that you're going to have nightmares about, the one we just did, I think that's interesting, at least. This isn't very interesting, but it's like the only way I can make sure that you do know that symbolic version of the chain rule. I think there's a lot to be said for the very informal stuff calculations we've been doing, but this is how I'm going to make sure you know the symbolic version too. All right, parts C and D are a little more challenging. Part C says the derivative of the function f of x raised to the 4th. Now we really need to start thinking about what's the outer function and what's the inner function. What do we think for this one? The stuff is the f of x. So I'm just going to write here, the inner one is the f of x. Do you guys agree? That's inside. And what's the outer function? Is x to the 4th. It's the function that takes that stuff and raises it to a power. This is a big leap, writing that x to the 4th down. And that's the important part for right now, is that the inside was f of x, and then how do you take that thing and raise it to the 4th? Well, you generally just give me the x to the 4th function, which says take whatever stuff you have and raise it to the 4th. So if you prefer, we could call it g of x is x to the 4th. And then if I write this thing out, maybe it'll clarify for anybody that doesn't see it. G of f of x equals g of, well, okay, we don't have to write it. F of x, I don't know what it is, but it's just f of x. But the g function says take whatever you give me and raise it to the 4th power. So this is really f of x to the 4. So we have built f of x to the 4th by decomposing it into two functions. And so basically we're just going to copy that same kind of rule that we did up above. But this is kind of like what Garrett said when he was used to using the letter z, but in a problem z wasn't the thing he was used to it being. Here g and f are reversed, right? Everything we did last class, g was the inner function and f was the outer. All right, well, we better be able to translate this rule up here at the top by swapping all the f's and the g's. So if I write this thing out again, maybe you can just do this in your head, but if you can't, g of f of x, I haven't written it, but I think it's a matter of just interchanging all the g's and f's. So what should it start with? It should be g prime of f of x times f prime of x. Okay, that's our, when the letters aren't the ones we're used to, that's the rule.
I guess it would be nice if there were some algebraic letters that were off limits for use without problems, so they could use policy outside of problems without. If they were like Z, would never be used in problems. Use Z outside of problems.
I never heard cross-contamination used to describe like the symbolic stuff we're doing, but I hear you.
Yeah, like something like a symbol. Yeah.
Okay, so let's give this a shot. This derivative down here equals. Okay, so we're going to do g prime. What's g prime for my function right here? 4x cubed, right? But now it's not just g prime of x, it's actually g prime of some stuff. So it's not 4x cubed, it's 4 f of x cubed. That's the stuff that goes in the parentheses, right? We're doing g prime, not of x, but of f of x. So instead of 4x cubed, it's 4 f of x cubed. 4 f of x cubed. Times, and then we're doing f prime of x. What is f prime of x? It's f prime of x. I don't know anything else about it. F. So that's what I put. I think that that's hard. Getting to that in your mind, I think it's a leap. So everybody was good with the derivative of g is 4x cubed, but we didn't want just g of anything. We wanted g of f of x. G is this 4x cubed function. Instead, it's 4 f of x cubed. And then we stuck on at the end in green, derivative of the stuff, derivative of the stuff. We still have to plug in x equals 1. That's going to be cake easy, but this is the hard part. Nikki?
How do we stop ourselves from taking the derivative of f, doing the derivative of x means one.
Yeah, good question. It feels like, we're going to plug x equals 1 in. The question is, when do we do it? And so here's the answer. Always at the end. It's always at the end. If you were to plug x equals 1 in now, then inside of here it would say f of 1, right? How much is f of 1? 4. Super. This is now 4 raised to the 4th. That's 256. Now it says the derivative of 256. What is it? 0. So if you plug in at the beginning, you're going to get 0 every single time because you're going to be taking the derivative of a number. So that, that's maybe one way to try to catch it. But the rule of thumb is you find your derivative with x's always, and only when you're done with all the calculus stuff with x's, you get to plug in the number. That's fine. That's fine. If f of 1, sorry, let's see, we're going to do f prime of 1. Is this thing in green? If f prime of 1 happened to be 0, then the answer would be 0, and that's okay. Okay, so for this one, we then just plug in. It should say 4 times f of 1 cubed times f prime of 1. Replacing all the x's with 1. That's the last step. And then let's get a number. How much is f of 1? 4. So we're doing 4 times 4 cubed, 256. So this is equal to 4 times 4 cubed times f prime of 1, negative 2. So negative 512 is our answer. Okay, and then part D. Am I wrong? Somebody check me. What did we get? 512? Okay.
Oh, okay. I thought it was 4 times 4 times 4.
Yeah, okay. All right, so that's that. Let's go to part D. It says the derivative of f. So the thing about the calculation stuff is that maybe you guys are impressed, but my second class, there's no way they'll be impressed because they'll say, oh, Ian just remembers that from the first class. They think that everything is like pre-planned and I cook the books. And so they don't get the joy of seeing me just like do these like amazing, unbelievable feats of calculation. All right, so part D, I have no space for it. Maybe you do. It says the derivative of f of x to the 4th. I'm going to squeeze this one down here. F of x to the 4th. Again, I think of inner function and I think of outer function. What is the inner function? It's x to the 4th. That's the inside, the innermost part. I'm going to call that g of x. And then what's the outer function? It's f of x. It's just the f function. I don't know anything else about it, but I know it's called f. So if you check what f of g of x is, let's see. So f takes something. I don't know what it is. So what is g of x in this case? So g of x is x to the fourth. So do you guys buy that we have built f of x to the fourth? That's what we wanted. The thing that we wanted is now built as a composition. And as soon as it's a composition, now it's looking familiar to me, and I can apply my chain rule. So then my derivative is equals, okay. So let's see, is this the normal version of the chain rule or the one with the letters swapped that we did on the right? This is the normal one. F is on the outside, that's what it was for our standard way of writing things. Okay, so we'll write the standard thing. F prime of g of x times g prime of x. It's the standard one with f's and g's. All right, so equals, all right, so f prime of, let's see, so g of x, what can I put? What is g of x? It's x to the fourth. So this is f prime of x to the fourth times g prime of, oh wait, sorry, and then g prime we actually know. What is the derivative of g? It's 4x cubed. So that right there is our almost final answer. The calculus is done now. So for the first step, f prime of g of x, we just replaced. Instead of g of x, we brought it back as x to the fourth, and then times the derivative of the stuff. Derivative of x to the fourth is 4x cubed. And I can't see it, but what are all the x's about to become? Okay, so we make all the x's 1s. F prime of 1 to the 4 times 4, 1 cubed. F prime of 1 times 4. And what is f prime of 1? -2. So -8 is our final answer. All right, what do we think of this kind of chain rule question? Yeah, there are many opportunities to get tripped up. And there's two basic things I'm going to ask you guys to do. One of them is the crazy first long derivative that we did, right? I needed a whole new piece of paper for it. And then the second is this kind of problem. And like I said, there's nothing super interesting about this kind of problem, but you know, I do think that this really makes it so that you can't just sort of memorize the special rules, right? We started with 4 special rules: sine of stuff, e to the stuff. I think that that's great. It'll take you pretty far. But you know, the chain rule is something more general than those 4 special rules. And so this kind of problem, I think, really pushes your mind to see if you can adapt the general chain rule to some crazy thing that I give you. All right, so we have 5 minutes. Maybe you guys can start right here on page 18 and see how far you can get with these problems.